So the conservation of linear momentum would mean that the resulting neutron star, which is formed in the center, must carry away the opposite linear momentum. So it gets a kick because of the asymmetric explosion. In fact, radio astronomers as well as optical astronomers have determined that many of the pulsars, which are essentially rotating neutron stars, indeed have very large linear motion, and this large linear motion is attributed to the kick they receive during the supernova explosion by virtue of conservation of linear momentum. Now, most astronomical data come to us in the form of light. In fact, the old astronomy essentially was a result of looking at astronomical objects through telescopes that received light from the heavenly objects. Newton, he was instrumental in discovering that white light, for example, light from the sun, when it passes through the prism, it undergoes dispersion because of which the white light is split into its constituent monochromatic colors, and the usual Vibgyor pattern of light comes out when the light passes through the prism. This dispersion plays a very, very important role in the spectroscopic analysis of light which comes from astronomical objects. For example, if you want to find out which star is hotter, then you have to study the light and you have to find out its spectrum, how much fraction of light is in the indigo, blue and violet, and how much in the red. Hotter the star is, the fraction of energy that is distributed in the lower wavelength like violet, blue will be larger. If the star is cooler, then fraction of its energy in the longer wavelength like yellow, red will be larger. So spectroscopic analysis, which essentially boils down to doing a dispersion of light into its various monochromatic colors, it plays an extremely important role in astronomy. Now, when Maxwell he gave his theory of electrodynamics, it turned out light is nothing but one special case of electromagnetic wave, which is that of very short wavelengths. From the days of Coulomb, physicists knew that if you have electric charges, then like electric charge they repel each other, while opposite electric charge they attract each other. Similarly, if you have moving charge particle, then moving charge particles, they have an effect on the compass needle, showing that the moving charge particles, they result into generation of magnetic field. All these things were neatly summarized by Maxwell in 19th century in the form of Maxwell's laws of electromagnetic fields, which essentially said that electric charge acts as a source of electric field, while moving electric charge acts as the source of magnetic field. Changing electric field results in magnetic field. Changing magnetic field results in electric field. And then Maxwell, from this kind of analysis, predicted that the changing electric field and changing magnetic field must propagate in the form of electromagnetic waves. And this prediction of Maxwell of propagating electric and magnetic fields, namely the electromagnetic waves, was confirmed by experiments done by Hertz. And it turned out that light, by which we see day-to-day objects around us, is nothing but a kind of electromagnetic waves with wavelengths varying from about 4,000 angstroms to about 9,000 angstroms. While there are electromagnetic waves with longer wavelength, for example, the TV set you have in your drawing room, that receives radio signals from a TV station antenna, and this radio waves, they are very, very long wavelength electromagnetic waves. They can have wavelengths going from few centimeters to as long as hundreds of meters. And essentially, whether it is light or or radio waves, classically they are nothing but fluctuating electric and magnetic field. And as physicists say that one of the uh, uh, most beautiful set of equations is this Maxwell's equation that represent electromagnetic waves. And as you can see that on the t-shirt it is said the Maxwell's equations are so beautiful that it is represented in biblical terms, that the God said, let there be Maxwell's equation, which resulted into light. And one of the classic application of Maxwell's equation is in the understanding of pulsars. If you recollect, I mentioned that after supernova explosion, very often at the core there is a birth of neutron star. Neutron stars, because of the conservation of angular momentum, they are spinning very rapidly. There is also another conservation called magnetic flux conservation, because of which the magnetic flux is conserved. Because neutron stars are highly dense objects, the resulting magnetic fields are very large. Now, here is a schematic diagram of a neutron star with magnetic lines of forces. So, the neutron star can be thought of as a dipole magnet, just like a bar magnet, but the magnetic field is very strong, of the order of 10 to the power 12 Gauss to 10 to the power 14 Gauss. Now, if the magnetic axis is not aligned with its spin axis, then as the neutron star spins about, the magnetic axis keeps precessing about the spin axis. Therefore, an observer who is static near the neutron star will see a changing magnetic field. But Maxwell's equation says that changing magnetic field results in electric field. So there are huge, gigantic electric fields created in the vicinity of a rotating magnetic dipole, namely the neutron star. And this huge electric field, they cause charged particles being ripped away from the surface of the neutron stars, and these charged particles, they accelerate because of the electric field and radiate predominantly in the direction of their motion, resulting in funnel-shaped radiation of electromagnetic waves. And because the magnetic axis is tilted with respect to the rotation axis, and we can see only if our line of sight is along the funnel, therefore we see pulse of electromagnetic radiation. As the funnel of electromagnetic radiation sweeps past our line of sight, we see a pulse of radiation. So this neutron star acts like a cosmic lighthouse, and the physics of pulsars, because of this model that it is a rotating neutron star, is essentially, it deals with solving the Maxwell's equation describing electromagnetic waves in the presence of charges. But all these were classical analysis of electromagnetic waves. Around 1904, it was realized that electromagnetic waves, or for that matter any object, has quantum mechanical properties. And Max Planck, he essentially thought of electromagnetic radiation as bundles of quanta of energy packets. So the quanta, if the electromagnetic waves has a frequency nu, then each quanta has energy h times nu, where h is today called the Planck's constant. And Einstein used this new proposition posed by Max Planck to explain photoelectric effect, in which if you have a metal like cesium or sodium, and when there is an incident electromagnetic wave, then if the frequency of the incident electromagnetic wave is high enough, it can knock the electron off from the metal surface, and Einstein, using the Planck hypothesis, explained the photoelectric effect. So in quantum theory, light also acts like a bunch of particles. Each such particle, or the quanta of electromagnetic radiation, today we call it photons. So the photoelectric effect, it essentially corroborated the picture that what we knew as classical electromagnetic radiation, in under certain circumstance, acts like a bunch of particles, each particle having an energy, the Planck's constant h, times the frequency of the electromagnetic wave.